This is our next subject after studying system of particles. In fact, rigid bodies are a subset of system of particles. They can be called a special type of system of particles, and this is based on the fact that we call the rigid body as a system of particles where the particles are rigidly connected to each other. Having said that, let's take a look at two different versions of the same scenario. Let's say that we have a system of particles that looks like a square, and there's a body fixed frame at the middle of this rigid, not the rigid body, but the system of particles. And in the next sequence, then the system of particles can move with respect to each other, and then this square can be a larger square. Now, if we have the same body fixed frame on the second sequence, and since this is body fixed frame, its location is the same, it's in the middle. The location of the corner part of the system will be different in the second sequence. However, if we are talking about the rigid body concept, then it should be the same because these particles are connected rigidly to each other. So this is a general understanding of system of particles, but in rigid body concept, if we have a square like that and a body fixed frame in the middle of that square, similar to this, if it moves to a different location, if it does a translational motion and moves to a different location, the location of the corner piece, for example, the point on the corner or the particle on the corner, with respect to the body fixed frame would stay the same. Even if there's a rotation of this rigid body, it has rotated to a new orientation, the frame rotates with the rigid body as it is a body fixed frame, and as a result of that, the location of the particle on the corner with respect to the body fixed frame stays the same. So this is the concept of rigid body, and this is actually the motion of rigid bodies. We can do a translation, we can do a rotation, changing the orientation. So we can say that this is an orientation change of theta from the ground. And also you can do a translation and fixed axis rotation. So in that case, what we are trying to say is, if we say that there is this origin of that rigid body at the frame location, fixed body frame location, we can draw a line between these two origins of the same rigid body at different locations, and this line shows us the translation, and then there's a rotation of the rigid body, or this could happen vice versa. First the rotation can happen and then translation can happen as well. This is actually the way that we investigate. In fact, in reality, what happens is rigid bodies usually translate and rotate simultaneously. They don't do one and then the other. They do it simultaneously. They don't do just translation and then rotation, but they translate and rotate at the same time most of the cases. But the way that we can investigate this is by partitioning this motion into parts like translation, pure translation part, pure rotation part, and this really helps us in our investigations of kinematics. And this is what we're going to study, plane kinematics of rigid bodies. That means we're going to study the motion of rigid bodies. And the type of motions that we will study are these two motions, as translational and rotational motion. The rotational motion is called the fixed axis motion or fixed axis rotation, and a combination of these two would be the general plane motion. Again, we are studying only the planar motion of rigid body systems. Now, the first thing that we're going to take a look at is the sorry about that. The first thing that we're going to take a look at is the translational motion. We can investigate the translational motion in two parts, as rectilinear and curvilinear translation. The difference in between two is that in rectilinear translation, the path of each point on the rigid body is a straight path. The magnitude is the same, the direction is the same, so these two lines here from A to A prime and B to B prime are parallel to each other, and their magnitudes are the same. As a result of that, if we say that this is the mass center, well, I'm not doing a good drawing here, but let's call this point G, and then there's that point G. The line in between these G and G prime would be the same. And remember that in system of particles we were talking about the acceleration of the mass center, AG, right? Now in a translational case, AG would be equal to the acceleration of any point. As long as there's no rotation of a rigid body motion, then the acceleration that is measured at any point of the rigid body would be the same. This is not true for system of particles. Remember that in system of particles, the particles can move relative to each other as well. They have independent motion from each other. But in rigid bodies, they don't have independent motion. They are rigidly connected to each other. Curvilinear case is the same. The acceleration measured at any point would be the same. The only difference in curvilinear motion is the path that each point follows is not necessarily a straight path. It could be a curved path, but if there's a curved path of any point from one location to the next location, the other points, any other points actually, path would be the same path. It cannot be different for curvilinear translation, if you're going to call it curvilinear translation. If it is different, then it's not curvilinear translation. In curvilinear translation, the motion of any point, the path of any point would be the same. And a good example of that is this special four-bar mechanism. It's a parallelogram. The reason that it's called parallelogram is that the link number 1 and link number 2 lengths are the same, and link number 3 and link number 4 lengths are the same as well. 3 and 4 are called the moving platforms frame and the ground platforms link. And these link lengths, if this is satisfied, this is a specific constraint, then the type of motion of this rigid body denoted with blue color is a curvilinear path, which means it doesn't rotate. If this is not satisfied, if it is a general four-bar mechanism, then you would expect it to translate and rotate. But if we can satisfy these certain, let's say, certain type of constraints, then the type of motion it's going to have for this point, for example, it will be a circular point, right? It will be a circular path. Nevertheless, it's not going to rotate because the path of the next point is the same circular path, because the radius of these are the same. Okay, so it will have the same circular path in that sense. It doesn't look the same the way that I draw it, but it's actually the same. So maybe I can just copy and paste it, and then drop it around here to show you that they have exactly the same type of circular paths at these 2 points. Anyways, then for we can move on to fixed axis rotation. And in fixed axis rotation, what happens is that we fix the rigid body at a specific point on the rigid body, and in this case this is the point A, and we introduce a revolute joint here, which enables the rotation of this rigid body above point A. In that case, the type of motion that this rigid body can do is only a fixed axis rotation. Now, if we consider point B, the type of path it's going to follow will be a circular path, and the radius of that path will be RAB. This is the radius it's going to have, and if the rigid body performs a motion with some theta dot, let's say, angular speed, then the linear speed of this B point will be RAB theta dot, right? And then if you're going to talk about only the tangential component of the acceleration, the type of acceleration it's going to have in the tangential direction will be RAB theta double dot, which is the angular acceleration. In fact, we're going to have also a normal part of this acceleration, right, towards the point A. But I'm not talking about it at the moment. It's just to make you see that any point on this rigid body would have a different velocity and a different acceleration, in fact. So if we are talking about a point C here, the radius of point C will be different, but it's going to experience the same theta dot and theta double dot angular velocity and angular acceleration. But then the velocity, linear velocity, and the acceleration of point C will be different than point P. And this is fixed axis rotation. In general plane motion, the rigid body performs both of these motions as fixed axis rotation and translational motion. As a result of that, because it does rotate, any point's velocity and acceleration would be different in this case. Now we can investigate this motion in a number of ways. We can first do a rotation about a fixed point, for example a B point, rotate it so that this is parallel to the next sequence line, and let's call this A double prime. And then we can move the rigid body from B to B prime. This is a way to investigate. However, we can choose a different way of investigation. So I will do a theta amount of rotation, by the way. We can do a different type of scenario to investigate the same type of motion. First, we can move from A to A prime, for example, and then if we do that, there is our B double prime location. And then we can rotate about A prime to rotate about A prime, rotate B double prime to B prime. And this is going to be a translation and then a rotation. Now, if you take a look at the paths that they follow towards that point, these paths should be the same. First of all, we do a translation, pure translation, and then a rotation. Okay. So this is a general plane motion, and a good example for these type of systems would be 4-bar mechanisms. This is again special 4-bar mechanism. This is called slider crank. There's the crank, which is doing a fixed axis rotation about this point. There's our slider, which is doing a translational motion, a straight path motion back and forth. And the coupler link is this blue link. And the type of motion this blue link does is rotational motion because of the crank, and the translational motion because of the slider. So it's a combined motion, which is called the general plane motion, doing both rotation and translation at the same time.